As we prepare to move into real trigonometry, we're going to need to talk about angles and how we measure angles, which is different in precalculus than it was in geometry, or it can be. So we want to start by remembering what an angle is. Now in geometry, we should have learned that an angle is actually just two rays with a common endpoint. Rays are the ones that have an endpoint and then go on forever in one direction. So two rays that start at the same place form an angle. In geometry, you may thus have been restricted to only angle measures between 0 and 180. Depending on how they emphasize that, you may or may not remember. We measure the angle between them based on how much of a circle it makes, which we're going to come back to later. The biggest difference between how we did this in geometry and how we're going to approach it in precalculus is that we're going to distinguish these two rays. We're going to call one of the rays the initial side and the other the terminal side. So there's a starting ray and an ending ray, and that way our angles actually have directionality as well as size. So you can actually have negative angles. If you're going clockwise, we consider that angle to be negative. Counterclockwise is a positive angle. So you will need to be able to distinguish between your initial side and your terminal side. Most of the time, we do this in precalculus by always putting the initial side as the positive x-axis. And that's one of the reasons we go counterclockwise for positive, because if we start on the x-axis, clockwise puts us in the first quadrant, for acute angles anyway. So when we start learning about angles, way back when you were tiny little children, we did degrees. You're probably familiar with degrees mostly. So each angle is considered to be part of a circle. 360 degrees is a full circle, and then your angle gets a measure based on how much of the circle it represents. This one is 30 degrees, or at least it is, depending on how your video scales. It's 30 degrees on my screen. So you're probably used to seeing, if we need more precise than the nearest degree, decimals for your degrees, 32.75 degrees, for example, which is pretty common. We use base 10, so it makes sense. Of course, then one wonders why there's 360 degrees in a circle and not, say, 100. But I didn't design this system. Traditionally, each degree was broken into actually 60 portions. Instead of multiples of 10, it was 60 minutes. So 1 minute is a 60th of a degree. Use the little apostrophe there to denote minutes. So 42.75, that's 42 and 3/4, which 3/4 of a degree is 45 minutes. So it would be 42 degrees, 45 minutes. You can also break the minutes down further if you need to into seconds. You may have seen angles written like this if you were ever looking at, say, a GPS feed. GPS angles are precise enough. They actually use minutes and seconds of a degree. As far as converting between decimal degrees and degrees, minutes, and seconds, it's mostly a matter of remembering what degrees are. So, or I should say minutes are. So 32.6 degrees, you've got the whole number portion, which is the 32. The 0.6, we need to convert that into minutes. So we just take the decimal portion, 0.6, and we multiply it by 60, which will tell us how many minutes we have. 32 degrees and 36 minutes. This worked out exactly in minutes, so there's no need to keep going. But we'll see one later that doesn't. If you have something that's already in degrees, minutes, and seconds, and you want to convert it into a decimal form, it's, again, just a matter of keeping in mind what minutes and seconds are. So 30 minutes, each one of those is a 60th. So we can turn that into a fraction, 30 over 60. And then 18 seconds, each second is 1/60th squared, or 3,600, 3,600. So 18 over 3,600. Really, to do this, I would put it into a calculator. And in this case, 505, 40.505. So let's do this one. Will not work out perfectly in the minutes place. So if you have an angle in degrees with a decimal and you need minutes and seconds, you can take the whole number portion, that's your degrees, 187. You need 215 to convert to minutes, So 215, or I should say 0.215 times 60 will give you 12.9. So that's 12 whole minutes and then zero point 0.9 of another minute. So again, we're going to take that decimal portion, that 0.9, multiply it by 60 again, which will give you 54 seconds. Unless you're doing really precise angle measures like astronomy, where you're measuring the angles between two different stars to figure out how far away they are, or GPS coordinates, I mean really precise stuff, you don't need usually to go past seconds. There isn't anything really past the second, so if you need to go more, you'll just use a decimal there on the seconds. But I don't think it'll come up in your work this year in my class. Oh, degrees are stupid. I think I mentioned that before. Why 360 degrees? It turns out 360 degrees makes a circle because the ancient Assyrians had a base 60 numbering system, and they thought there were 360 days in the year. So literally the number of degrees we have in a circle is because people were wrong about how long a year was. It's 365, right, days in a year. They were close. I mean, for how long ago that was, it's fine. It is what it is. But degrees are silly. In fact, anything called degrees, including like temperature, where we do Fahrenheit and Celsius, what the degrees, the symbol, and the name means is that it has no relation to anything actual. It's just we marked it off and decided how many marks we wanted to make, and it's completely arbitrary. So degrees has no relation to reality other than we decided to split our circle into 360 degrees. To wit, we're going to learn how to use radians starting now and proceeding forward. You will need to make sure when you're using an electronic tool like a calculator or an online graphing tool or whatever to make sure you remember whether you're using degrees or radians because they're not the same. But radians is an angle measure that is based on something that actually exists. And that's why it's called radian, because actually the angle measure is based on how a circle is related to its radius. So if you imagine an angle, so that when you made a circle, the length of the arc around the outside, this S over here, was the same as the length of the radius, we call that angle measure 1 radian. So 2 radians would be enough of the circle so that the arc was twice as long as the radius. If you remember your geometry, 1 full time around the circle is, the circumference of a circle is 2 pi. So 2 pi radians, that's about 6 1/4. It's 6.28 actually. 6 1/4 radians then is an entire circle, or pi radians is a half a circle. Oh, right. Yeah. So 360 degrees is equal to 2 pi radians, which, again, is about 6.28. That's approximate because pi is irrational. So the disadvantage is the numbers are yuckier, but the advantage is if we leave it in terms of pi, then pi is a half a circle, and when we have a fraction of pi, like 1/3 of pi, we know that's 1/3 of a half of a circle. So as long as we keep it to fractions multiplied by pi, it'll give us actually a better picture of how much of a circle it is than degrees does, and the numbers stay small. If you need to use this in a formula where you need an actual answer, you can always multiply it by pi using a calculator. Normally, what you want to keep in your mind is that 180 degrees is the same as pi radians. And we're going to use that when we convert, and we're going to use it when we start trying to figure out where we are on a circle. All right, so as far as converting to and from radians, hopefully you're taking chemistry and you've done some unit conversions. If not, it's not really so bad. But to convert from 120 degrees to radians, you're basically going to divide by the unit that you have, and you're going to multiply by an equivalent number in the new unit. So the equivalency there is 180 degrees and pi radians. If you build a fraction that has 180 degrees on the bottom and pi radians on the top, those are the same, that fraction is equal to 1. Multiplying by 1 does not change your answer. So 120 times pi over 180 will give you the same actual answer because pi radians and 180 degrees are the same. That's multiplying by 1. So when you do, the degrees cancel. 120 over 180 is 2/3, and then you have the pi. So 2/3 pi. 120 degrees is 2/3 pi. If we do this backwards, you've got 5/3 pi radians, for example. In this case, we're going to divide by pi radians, and we're going to multiply by 180. The pi radians cancels, the pi and the radians. So all we need is 5/3 of 180. 180 divided by 3 is 60, times 5 is 300. So 300 degrees. Divide by what you have, multiply by what you want. In this case, the units we're talking about. So you're always going to use pi and 180. Divide by the one you have, multiply by the one you want. That way the one you have cancels, and you end up with the one you want. Coterminal angles is a subject that we will talk about or use this unit. Now that we have set our initial sides to be on the positive x-axis, you can actually have two angles that end in the same place. So 2/3 pi, that's 2/3 of a half a circle, so it ends up about right there. That's 2/3 pi. Now it turns out if you have 8/3 pi, 6/3 is 2 pi, that's one full circle. So 8/3 is an entire circle plus another 2 pi. 2/3 pi, I should say. Sorry, 2 pi plus 2/3 of pi. And you'll find that these two angles end in the same place. So they have the same initial side, and they have the same terminal side, but they're not exactly the same angle, because if you're doing things like how far does a wheel turn, or how many times has this person rolled around, I don't know, radar sweeps, anytime you're actually measuring circular motion, you want to be able to distinguish between these two rotations. But the word we use then is coterminal. One of them has traveled much further, but they ended up in the same place. Uh-oh, I'm out of time. We need a formula for arc length. In radians, it's nice and simple because the definition of radians is that the radian degree tells you the arc length if you multiply it by the radius, or radian measure, I should say. So S equals R theta will give you your arc length. In degrees, the formula is pi r squared over 180, which is not nearly as nice. It's usable, so if you really like degrees, or if you have a problem that's in degrees, these formulas are in your book. Area of sectors, a sector is like a pie slice of a circle. In radians, basically we're going to take pi r squared, that's a full circle, multiply it by the part of the circle we have, or theta over 2 pi. So the formula ends up being S is r squared theta over 2, or 1/2 r squared theta. It's not too bad. Area is always a bit worse than lengths, but it's a little yuckier, but not too bad. In degrees, if you're talking about how much of a circle you have, it's pi over 360, and that doesn't reduce at all, so you end up with pi r squared theta over 360, which is awful. Anyway, that's area of sector and arc length, which are formulas you're going to use in your homework, which is 1 through 71, first and last. Yeah, well, all right. That's the entirety of this lesson. Enjoy.